Hello, my name is Youssef, and I'm here to teach you some of the basics of the Keysight EDUX 1052A oscilloscope. I will be using our Regel DG 1022 function generator to provide a 1 kHz 6-volt peak-to-peak signal to test my circuit. I'm using a series RC circuit with a 2.7 kilo ohm resistor and a 100 nanofarad capacitor. Channel 1 of the oscilloscope is set to measure the source, which also represents the nodal voltage at node 1. And channel 2 is set to measure across the capacitor, which represents the nodal voltage at node 2. The probe for channel 1 is connected to the resistor at the same point as the positive from the function generator. The ground for the probe is connected to the ground power rail, the overall ground for the circuit, which is the same as the bottom of the capacitor. The probe for channel 2 is connected to the side of the resistor or connects with the capacitor, and its ground also is connected to the bottom of the capacitor along with the negative from the function generator. Let's power on the oscilloscope and let's get going. The first thing I'm going to do is press the default setup button, and then the back button. This should remove any specialized settings which a previous user may have had set up, and reset them to the baseline of the oscilloscope. Here you can see that the channel 1 light is on. This means that we are only viewing channel 1 at this time. Later we'll turn on channel 2 and set that one up as well. The signal can be seen, but it's pretty flat as the voltage scale is set to a large value per division right now. In order to adjust this, turn the larger knob under vertical. I'm going to set the vertical sensitivity to 1 volt per division. This value can be seen in the upper left corner of the screen. With this setting, you can see that the waveform now takes up 6 full vertical divisions on the screen, or 6 divisions multiplied by 1 volt per division equals 6 volts peak to peak. The small knob under channel 1 will adjust the vertical position of the waveform. In this case, we have no DC bias. You want to ensure that the ground is at the center of the screen. Notice that the arrow with the ground symbol and the number 1 on the left, this is what you are adjusting. If the waveform is off the screen, you'll see the 1 either up or down depending on if the waveform is off the screen to the top or to the bottom. Make the adjustment to center the waveform. You can also center the waveform by pressing down on that same smaller knob. Let's move on to the horizontal settings. On the horizontal axis, I like to have 2 to 3 waveforms on the screen. In order to adjust that, turn the large knob where it says horizontal. Both channels must use the same horizontal scale. In this case, I've set it to 200 microseconds per division. The small knob to the right will adjust the position so that you can ensure the waveform starts at the center of the crosshairs. Note that 1 full waveform now takes up 5 full divisions in the x direction, or 5 divisions multiplied by 200 microseconds per division is 1 millisecond of time. What if my oscilloscope looks like this? Don't be too worried. Let's take a step back and see what we know about the screen. It's important to remember that the horizontal sensitivity is at the top of the oscilloscope display. It represents the increment of each major horizontal grid line. In this case, it is very large compared to the period of our signal. We are operating at a 1 kHz frequency signal, meaning there are 1,000 cycles of the sine wave per second. The period represents how long it takes for one cycle. The period for our circuit is 1 millisecond. To see less cycles, let's use the same horizontal knob to decrease the horizontal sensitivity. Perfect. I'm now going to turn on channel 2 and set its voltage level to be the same as channel 1. Now that we have both channels turned on, let's make sure both signals are centered around 0 volts. You can do this by selecting each signal, 1 or 2, and pressing down on the smaller knob under vertical. You can see that there is a phase difference. This is due to the capacitor. We can see on the oscilloscope that the voltage of the capacitor signal is lagging behind the voltage of the source. There is also a slight difference in the voltages of the two signals, the voltage of the source and the voltage of the capacitor. That is because we also have a series resistor in the circuit. The source voltage will divide between both series components. Let's press the measure button. Here we can select from various types of measurements. The source default is channel 1. However, you can also do measurements on channel 2. Pressing the type button will bring up the long list of available measurements. Use the small knob on the entry section to move up and down to the desired measurement. I'm going to select VPP. Pressing the Add Measurement button will add it to the bottom of the screen. This is the peak-to-peak voltage. You can see the voltage of the source signal isn't exactly 6.0 volts being supplied by the function generator. We don't calibrate our equipment as that is a very expensive process, so there might be slight variation in the values. I'm now going to add in a peak-to-peak voltage measurement for channel 2. You can see that it is a little bit lower than channel 1 due to the voltage drop across that series resistor. I can also measure the phase difference between the two signals. Using the same knob under entry, navigate to the measurement called phase. For some measurements, you might want to also click the settings option before finalizing the measurement. Here I want to know the phase of channel 2 with respect to channel 1, so I will enter that order in the settings. My result of negative 60 degrees is telling me that channel 2 is lagging behind by 60 degrees. If you want a clear measurement, press the Clear Measure button. Then press the button next to the measurement you want to remove. You can also clear all measurements right here. This will remove all measurements. The last function that is typically used in introductory courses is the Math button. This is located at the bottom left of the panel, and it comes with its own two knobs. Press the Math button to see what options are available. Typically for functions, you'll want the displayed option. Next, select the operator. Add and subtract are the most widely used. You can also select the order for your signals, so channel 1 minus channel 2, or channel 2 minus channel 1. In this case, I'm going to subtract the two signals, channel 1 minus channel 2. Remember that I'm subtracting the two nodal voltages, and my resulting signal is the voltage of the component in between them. That is our 2.7 kilo ohm resistor. The scale can be adjusted using the knob right above the Math button. I've set it to the same as the vertical scale for channel 1 and channel 2. The knob right below the Math button can shift the vertical offset. Just as before, let's make sure our signal is centered at 0 by pressing in on the knob. You can also use the measurement function on the Math channel. Let's try adding a peak-to-peak measurement on the Math channel. The Add Measurement option will look similar to before, and under Source you can now find the Math signal. Adding measurement values to the Math signal lets you double-check your simulated and calculated results. Use what you know about circuit configurations to reason the obtained values. Pressing the Math button again will turn it off. Remember to always turn off the equipment when you are done, and thank you for watching.